A lithium-ion battery is a member of a family of rechargeable battery types in which lithium ions move from the negative electrode to the positive electrode during discharge and back when charging. Li-ion batteries use an intercalated lithium compound as the electrode material, compared to the metallic lithium used in non-rechargeable lithium battery. Lithium-ion batteries are common in consumer electronics. They are one of the most popular types of rechargeable batteries for portable electronics, with a high energy density, no memory effect, and only a slow loss of charge when not in use. Beyond consumer electronics, LIBs are also growing in popularity for military, electric vehicle and aerospace applications. For example, lithium-ion batteries are becoming a common replacement for the lead-acid batteries that have been used historically for golf carts and utility vehicles. Instead of heavy lead plates and acid electrolyte, the trend is to use lightweight lithium-ion battery packs that can provide the same voltage as lead-acid batteries, so no modification to the vehicle's drive system is required. Chemistry, performance, cost and safety characteristics vary across LIB types. Handheld electronics mostly use LIBs based on lithium cobalt oxide, LiCoO2, which offers high energy density, but presents safety risks, especially when damaged. Lithium iron phosphate, lithium manganese oxide and lithium nickel manganese cobalt oxide offer lower energy density, but longer lives and inherent safety. Such batteries are widely used for electric tools, medical equipment and other roles. NMC in particular is a leading contender for automotive applications. Lithium nickel cobalt aluminum oxide and lithium titanate are specialty designs aimed at particular niche roles. Lithium-ion batteries can be dangerous under some conditions and can pose a safety hazard since they contain, unlike other rechargeable batteries, a flammable electrolyte and are also kept pressurized. Because of this, the testing standards for these batteries are more stringent than those for acid electrolyte batteries, requiring both a broader range of test conditions and additional battery-specific tests. This is in response to reported accidents and failures, and there have been battery-related recalls by some companies. Terminology. Although the word battery is a common term to describe an electrochemical storage system, international industry standards differentiate between a cell and a battery. A secondary cell is a basic electrochemical unit that contains the basic components, such as electrodes, separator, and electrolyte. In the case of secondary lithium-ion cells, this is the single cylindrical, prismatic or pouch unit, that provides an average potential difference at its terminals of 3.7 V for LiCoO2 and 3.3 V for LiFePO4. A secondary battery, or battery pack, is a collection of cells or cell assemblies which are ready for use, as it contains an appropriate housing, electrical interconnections, and possibly electronics to control and protect the cells from failure. In this regard, the simplest battery is a single cell with perhaps a small electronic circuit for protection. In many cases, distinguishing between cell and battery is not important. However, this should be done when dealing with specific applications, for example, battery electric vehicles, where battery may indicate a high-voltage system of 400 V, and not a single cell. The term module is often used as an intermediate topology, with the understanding that a battery pack is made of modules, and modules are composed of individual cells. History. Before commercial introduction. Lithium batteries were first proposed by M.S. Whittingham, now at Binghamton University, while working for Exxon in the 1970s. Whittingham used titanium, sulfide and lithium metal as the electrodes. Reversible intercalation in graphite and intercalation into cathodic oxides was discovered in the 1970s by J. O. Biesenhard at TU Munich. Biesenhard proposed its application in lithium cells. Electrolyte decomposition and solvent co-intercalation into graphite were severe early drawbacks for battery life. Primary lithium batteries with metallic lithium-negative electrodes pose safety issues. As a result, lithium-ion batteries were developed in which both electrodes are made of a material containing lithium ions. At Oxford University, England, in 1979, John Goodenough and Koichi Mizashima demonstrated a rechargeable cell with voltage in the 4V range using lithium cobalt oxide, LiCoO2, as the positive electrode and lithium metal as the negative electrode. This innovation provided the positive electrode material that made LIBs possible. LiCoO2 is a stable positive electrode material which acts as a donor of lithium ions, which means that it can be used with a negative electrode material other than lithium metal. By enabling the use of stable and easy-to-handle negative electrode materials, LiCoO2 opened a whole new range of possibilities for novel rechargeable battery systems. In 1977, Samar Basu demonstrated electrochemical intercalation of lithium in graphite at the University of Pennsylvania. This led to the development of a workable lithium intercalated graphite electrode at Bell Labs, LIC-6, to provide an alternative to the lithium metal electrode battery. In 1980, Rachid Yasami demonstrated the reversible electrochemical intercalation of lithium and graphite. The organic electrolytes available at the time would decompose during charging with a graphite negative electrode, slowing the development of a rechargeable lithium graphite battery. Yasami used a solid electrolyte to demonstrate that lithium could be reversibly intercalated in graphite through an electrochemical mechanism. The graphite electrode discovered by Yasami is currently the most commonly used electrode in commercial lithium-ion batteries. In 1983, Michael M. Thackeray, Goodenough, and co-workers identified manganese spinel as a positive electrode material. Spinel showed great promise, given its low cost, good electronic and lithium-ion conductivity, and three-dimensional structure, which gives it good structural stability. Although pure manganese spinel fades with cycling, this can be overcome with chemical modification of the material. As of 2013, manganese spinel was used in commercial cells. In 1985, Akira Yoshino assembled a prototype cell using carbonaceous material into which lithium ions could be inserted as one electrode, and lithium cobalt oxide, LiCoO2, which is stable in air, as the other. By using materials without metallic lithium, safety was dramatically improved. LiCoO2 enabled industrial-scale production and represents the birth of the current lithium-ion battery. In 1989, Goodenough and Arumugal Manthiram of the University of Texas at Austin showed that positive electrodes containing polyanions, for example, sulfates, produce higher voltages than oxides due to the induction effect of the polyanion. From commercial introduction, the performance and capacity of lithium-ion batteries increases as development progresses. In 1991, Sony and Asahi Kasei released the first commercial lithium-ion battery. In 1996, Goodenough, Akshay Paddy and co-workers proposed lithium iron phosphate, LiFePO4, and other phosphoolivines as positive electrode materials. In 2002, Yedming Chiang and his group at MIT showed a substantial improvement in the performance of lithium batteries by boosting the material's conductivity by doping it with aluminium, niobium and zirconium. The exact mechanism causing the increase became the subject of widespread debate. In 2004, Chiang again increased performance by utilizing iron 3 phosphate particles of less than 100 nanometers in diameter. This decreased particle density almost 100-fold, increased the positive electrode's surface area and improved capacity and performance. Commercialization led to a rapid growth in the market for higher capacity LIBs, as well as a patent infringement battle between Chiang and Goodenough. As of 2011, lithium-ion batteries accounted for 66% of all portable secondary battery sales in Japan. In June 2012, John Goodenough, Rachid Yasami and Akira Yoshino received the 2012 IEEE Medal for Environmental and Safety Technologies for developing the lithium-ion battery. By 2013, the lithium rechargeable battery had progressed to a lithium vanadium phosphate battery to increase energy efficiency in the forward and reverse reaction. In 2014, John Goodenough, Yoshio Nishi, Rachid Yasami and Akira Yoshino were awarded by the National Academy of Engineering for pioneering and leading the groundwork for today's unregistered trademark S lithium-ion battery. The prize, which is in its 25th year, includes a $500,000 award. In 2014, batteries started to have 20% higher capacity than those previously available, with a silicon anode rather than graphite anode, were being delivered to smartphone manufacturers. Construction. The three primary functional components of a lithium-ion battery are the positive and negative electrodes and electrolyte. Generally, the negative electrode of a conventional lithium-ion cell is made from carbon. The positive electrode is a metal oxide, and the electrolyte is a lithium salt in an organic solvent. The electrochemical roles of the electrodes reverse between anode and cathode, depending on the direction of current flow through the cell. The most commercially popular negative electrode is graphite. The positive electrode is generally one of three materials: a layered oxide, a polyanion or a spinel. The electrolyte is typically a mixture of organic carbonates such as ethylene carbonate or diethyl carbonate containing complexes of lithium ions. These non-aqueous electrolytes generally use non-coordinating anion salts such as lithium hexafluorophosphate, LiPF6, lithium hexafluosinate monohydrate, LiSF6, lithium perchlorate, LiClO4, lithium tetrafluoroborate, LiBF4, and lithium triflate, LiCf3SO3. Depending on materials choices, the voltage, energy density, life and safety of a lithium-ion battery can change dramatically. Recently, novel architectures using nanotechnology have been employed to improve performance. Pure lithium is highly reactive. It reacts vigorously with water to form lithium hydroxide and hydrogen gas. Thus, a non-aqueous electrolyte is typically used, and a sealed container rigidly excludes moisture from the battery pack. Lithium-ion batteries are more expensive than NICD batteries but operate over a wider temperature range with higher energy densities. They require a protective circuit to limit peak voltage. For notebooks or laptops, lithium-ion cells are supplied as part of a battery pack with temperature sensors, voltage converter regulator circuit, voltage tap, battery charge state monitor and a main connector. These components monitor the state of charge and current in and out of each cell, capacities of each individual cell, temperature of each cell and minimize the risk of short circuits. Shapes. Li-ion cells are available in various shapes, which can generally be divided into four groups: small cylindrical, large cylindrical, pouch, prismatic. Cells with a cylindrical shape are made in a characteristic Swiss roll manner, which means it is a single long sandwich of positive electrode, separator, negative electrode and separator are rolled into a single spool. The main disadvantage of this method of construction is that the cell will have a higher series inductance. The absence of a case gives pouch cells the highest gravimetric energy density. However, for many practical applications they still require an external means of containment to prevent expansion when their state of charge level is high, and for general structural stability of the battery pack of which they are part. Since 2011 several research groups have announced demonstrations of lithium-ion flow batteries that suspend the cathode or anode material in an aqueous or organic solution. Electrochemistry. The participants in the electrochemical reactions in a lithium-ion battery are the negative and positive electrodes, with the electrolyte providing a conductive medium for lithium ions to move between the electrodes. Both electrodes allow lithium ions to move in and out of their interiors. During insertion, ions move into the electrode. During the reverse process, extraction, ions move back out. When a lithium-ion-based cell is discharging, the positive lithium-ion moves from the negative electrode and enters the positive electrode. When the cell is charging, the reverse occurs. Useful work is performed when electrons flow through a closed external circuit. The following equations show one example of the chemistry, in units of moles, making it possible to use coefficient. The positive electrode half reaction is. The negative electrode half reaction is. The overall reaction has its limits. Overdischarge supersaturates lithium cobalt oxide, leading to the production of lithium oxide, possibly by the following irreversible reaction. Overcharge up to 5.2 volts leads to the synthesis of cobalt 4 oxide, as evidenced by X-ray diffraction. In a lithium-ion battery, the lithium ions are transported to and from the positive or negative electrodes by oxidizing the transition metal, cobalt, in Li, 1x-Co, 2 from Co3+ to Co4+ during charge, and reduced from Co4+ to Co3+ during discharge. The cobalt electrode reaction is only reversible for X less than 0.5, limiting the depth of discharge allowable. This chemistry was used in the Li-ion cells developed by Sony in 1990. The cell's energy is equal to the voltage times the charge. Each gram of lithium represents Faraday's constant /6.941 or 13,901 coulombs. At 3V, this gives 41.7 kilojoules per gram of lithium, or 11.6 kilowatt-hours per kg. This is a bit more than the heat of combustion of gasoline, but does not consider the other materials that go into a lithium battery and that make lithium batteries many times heavier per unit of energy. Electrolytes. The cell voltages given in the electrochemistry section are larger than the potential at which aqueous solutions will electrolyze. Liquid electrolytes in lithium-ion batteries consist of lithium salts, such as LiPF6, LiBF, 4 or LiClO, 4N inorganic solvent, such as ethylene carbonate, dimethyl carbonate, and diethyl carbonate. A liquid electrolyte acts as a carrier between the positive and negative electrodes when current flows through an external circuit. Typical conductivities of liquid electrolyte at room temperature are in the range of 10 millisecond per centimeter, increasing by approximately 30–40% at 40 AA degrees Celsius and decreasing slightly at 0 AA degrees Celsius. Organic solvents easily decompose on the negative electrodes during charge. When appropriate organic solvents are used as the electrolyte, the solvent decomposes on initial charging and forms a solid layer called the solid electrolyte interface, which is electrically insulating yet provides significant ionic conductivity. The interface prevents further decomposition of the electrolyte after the second charge. For example, ethylene carbonate is decomposed at a relatively high voltage, 0.7 eV versus lithium, and forms a dense and stable interface. Composite electrolytes based on PoE, developed by Sysdek al., provide a relatively stable interface. It can be either solid and be applied in dry Li polymer cells, or liquid and be applied in regular Li-ion cells. Room temperature ionic liquids are another approach to limiting the flammability and volatility of organic electrolytes. Charge and discharge. During discharge, lithium ions Li+ carry the current from the negative to the positive electrode, through the non-aqueous electrolyte and separator diaphragm. During charging, an external electrical power source applies an over-voltage than that produced by the battery, forcing the current to pass in the reverse direction. The lithium ions then migrate from the positive to the negative electrode, where they become embedded in the porous electrode material in a process known as intercalation. Charging procedure. The charging procedures for single Li-ion cells, and complete Li-ion batteries, are slightly different. A single Li-ion cell is charged in 2 stages: constant current, voltage source. A Li-ion battery is charged in 3 stages: constant current, balance, voltage source. During the constant current phase, the charger applies a constant current to the battery at a steadily increasing voltage, until the voltage limit per cell is reached. During the balance phase, the charger reduces the charging current while the state of charge of individual cells is brought to the same level by a balancing circuit, until the battery is balanced. Some fast chargers skip this stage. Some chargers accomplish the balance by charging each cell independently. During the constant voltage phase, the charger applies a voltage equal to the maximum cell voltage times the number of cells in series to the battery, as the current gradually declines towards zero, until the current is below a set threshold of about 3% of initial constant charge current. Periodic topping charge about once per 500 hours. Top charging is recommended to be initiated when voltage goes below 4.05 V cell. Failure to follow current and voltage limitations can result in an explosion. Charging at high and low temperatures. Charging temperature limits for Li-ion are stricter than the operating limits. Lithium-ion chemistry performs well at elevated temperatures, but prolonged exposure to heat reduces battery life. Li-ion batteries offer good charging performance at cooler temperatures and may even allow fast charging within a temperature range of 5 to 45 degrees Celsius. Charging should be performed within this temperature range. At temperatures from 0 to 5 degrees Celsius, charging is possible, but the charge current should be reduced. During a low temperature charge, the slight temperature rise above ambient due to the internal cell resistance is beneficial. High temperatures during charging may lead to battery degradation, and charging at temperatures above 45 degrees Celsius will degrade battery performance, whereas at lower temperatures the internal resistance of the battery may increase, resulting in slower charging and thus longer charging times. Consumer-grade lithium-ion batteries should not be charged at temperatures below 0 degrees Celsius. Although a battery pack may appear to be charging normally, electroplating of metallic lithium can occur at the negative electrode during a sub-freezing charge, and may not be removable even by repeated cycling. Most devices equipped with Li-ion batteries do not allow charging outside of 0-45 degrees Celsius for safety reasons, except for mobile phones that may allow some degree of charging when they detect an emergency call in progress. Production. Industry produced about 660 million cylindrical lithium-ion cells in 2012. The 18650 format is by far the most popular for cylindrical cells. If Tesla meets its goal of shipping 40,000 Model S electric cars in 2014, and if the 85 kWh battery, which uses 7,000 of these cells, proves as popular overseas as it was in the US, in 2014 the Model S alone would use almost 40% of global cylindrical battery production. Production is gradually shifting to higher capacity 3000 plus mR cells. Annual flat polymer cell demand was expected to exceed 700 million in 2013. Tesla Motors is planning on building the world's largest lithium-ion battery factory called the Gigafactory in the latter half of the 2010s. The factory would be approximately 10 million square feet in size and is planned to be able to produce a large enough quantity of cells to be able to build 500,000 vehicle battery packs per year. Specifications: specific energy density, 100 to 250 Wh per kilogram, volumetric energy density, 250 to 620 Wh, specific power density, 300 to 1500 watts per kilogram. Because lithium-ion batteries can have a variety of positive and negative electrode materials, the energy density and voltage vary accordingly. The open circuit voltage is higher than aqueous batteries. The internal resistance of widely used Li-2 batteries is higher than that of nickel metal hydride, nickel-cadmium, Li-4, and lithium polymer cells. Internal resistance increases with both cycling and age. Rising internal resistance causes the voltage at the terminals to drop under load, which reduces the maximum current draw. Eventually, increasing resistance means that the battery can no longer operate for an adequate period. Batteries with a lithium iron phosphate positive and graphite negative electrodes have a nominal open circuit voltage of 3.2 V and a typical charging voltage of 3.6 V. Lithium nickel manganese cobalt oxide positives with graphite negatives have a 3.7 V nominal voltage with a 4.2 V maximum while charging. The charging procedure is performed at constant voltage with current limiting circuitry. Typically, the charge is terminated at 3% of the initial charge current. In the past, lithium-ion batteries could not be fast charged and needed at least 2 hours to fully charge. Current generation cells can be fully charged in 45 minutes or less. Materials of commercial cells. The increasing demand for batteries has led vendors and academics to focus on improving the energy density, operating temperature, safety, durability, charging time, output power, and cost of lithium-ion battery solutions. The following materials have been used in commercially available cells. Research into other materials continues. Positive electrode, negative electrode, uses. Li-ion batteries provide lightweight, high-energy density power sources for a variety of devices. To power larger devices, such as electric cars, Connecting many small batteries in a parallel circuit is more effective and more efficient than connecting a single large battery. Such devices include portable devices. These include mobile phones and smartphones, laptops and tablets, digital cameras and camcorders, electronic cigarettes, handheld game consoles and torches. Power tools. Li-ion batteries are used in tools such as cordless drills, sanders, saws and a variety of garden equipment including whippersnippers and hedge trimmers. Electric vehicles. Because of their lightweight Li-ion batteries are used for energy storage for many electric vehicles, for everything from electric cars to pedelecs, from hybrid vehicles to advanced electric wheelchairs, from radio-controlled models and model aircraft to the Mars Curiosity rover. Li-ion batteries are used in telecommunications applications. Secondary non-aqueous lithium batteries provide reliable backup power to load equipment located in a network environment of a typical telecommunications service provider. Li-ion batteries compliant with specific technical criteria are recommended for deployment in the outside planted locations such as controlled environmental vaults, electronic equipment enclosures, and huts, and in uncontrolled structures such as cabinets. In such applications, Li-ion battery users require detailed, battery-specific hazardous material information, plus appropriate firefighting procedures, to meet regulatory requirements and to protect employees and surrounding equipment. Self-discharge. Batteries gradually self-discharge even if not connected and delivering current. Li-class rechargeable batteries have a self-discharge rate typically stated by manufacturers to be 1.5 to 2% per month. The rate increases with temperature and state of charge. A 2004 study found that for most cycling conditions self-discharge was primarily time-dependent. However, after several months of stand-on open circuit or float charge, state of charge-dependent losses became significant. The self-discharge rate did not increase monotonically with state of charge, but dropped somewhat at intermediate states of charge. Self-discharge rates may increase as batteries age. For comparison, the self-discharge rate is over 30% per month for common nickel metal hydride batteries, dropping to about 1.25% per month for low self-discharge NiMH batteries, and 10% per month in nickel-cadmium batteries. Battery life. Rechargeable battery life is often stated in number of charge cycles, but depth of discharge is usually not explicitly stated. Apple Incorporated clarified that a charge cycle means using all the battery's capacity, but not necessarily by full charge and discharge. For example, using half the charge of a fully charged battery, charging it, and then using the same amount of charge again count as a single charge cycle. Manufacturer's information implies that the life of a battery that is not abused depends upon the number of charge cycles it undergoes, specifying typical battery capacity in terms of number of cycles, with no mention of age of the battery. Research by Professor Jeff Dan of Dalhousie University suggests this common industry practice of merely counting cycles, ignoring the effect of age, is a poor predictor of real-world battery life. In particular, a major contributor to the degradation of Li-ion cell is the length of time they spend sitting at full charge, and with continuous cycle testing the cells are not left sitting with a full state of charge for any significant length of time. Battery performance is rarely specified over more than 500 cycles. This means that batteries of mobile phones, or other handheld devices in daily use, are not expected to last longer than 3 years. But it is also quite possible to obtain lithium-ion batteries based on carbon anodes with more than 10.000 cycles. Batteries may last longer if not stored fully discharged. As the battery self-discharges over time, its voltage gradually diminishes. When depleted below the low voltage threshold of the protection circuit, it will be disconnected and cannot be further discharged until recharged. This is because as the discharge progresses, the metallic contents of the cell are plated onto its internal structure, creating an unwanted discharge path. The rate of degradation of lithium-ion batteries is strongly temperature dependent. They degrade much faster if stored or used at higher temperatures. The carbon-negative electrode of the cell also generates heat. High charge levels and elevated temperatures hasten capacity loss. Poor ventilation may increase temperatures, further shortening battery life. Loss rates vary by temperature: 6% loss at 0 AA degrees Celsius, 20% at 25 AA degrees Celsius, and 35% at 40 AA degrees Celsius. In contrast, the calendar life of LiFePO4 cells is not affected by high charge states. They may be stored in a refrigerator. Charging forms deposits inside the electrolyte that inhibit ion transport. The increase in internal resistance reduces the cell's ability to deliver current. This problem is more pronounced in high current applications. Conditioning: the need to condition NICD and NIMH batteries has incorrectly leaked into folklore surrounding Li-ion batteries. The recommendation for the older technologies is to leave the device plugged in for 7 or 8 hours, even if fully charged. This may be a confusion of battery software calibration instructions with the conditioning instructions for NICD and NIMH batteries. The software of a typical smartphone, for example, learns how to accurately gauge the battery's life by watching it discharge, and leaving it on the charger produces a series of micro-discharges that the software can watch and learn from. Multi-cell devices: Li-ion batteries require a battery management system to prevent operation outside each cell's safe operating area and to balance cells to eliminate state of charge mismatches, thereby significantly improving battery efficiency and increasing overall capacity. As the number of cells and load currents increase, the potential for mismatch increases. The two kinds of mismatch are state of charge and capacity energy. Though SOC is more common, each problem limits pack charge capacity to that of the weakest cell. Safety: if overheated or overcharged, Li-ion batteries may suffer thermal runaway and cell rupture. In extreme cases this can lead to combustion. To reduce these risks, lithium-ion battery packs contain fail-safe circuitry that disconnects the battery when its voltage is outside the safe range of 3 V per cell. When stored for long periods, the small current draw of the protection circuitry may drain the battery below its shut-off voltage. Normal charges may then be useless. Many types of lithium-ion cells cannot be charged safely below 0 AA degrees Celsius. Other safety features are required in each cell: shutdown separator, tear-away tab, vent, thermal interrupt. These devices occupy useful space inside the cells, add additional points of failure, and irreversibly disable the cell when activated. They are required because the negative electrode produces heat during use, while the positive electrode may produce oxygen. These devices and improved electrode designs eliminate the risk of fire or explosion. Further, these features increase costs compared to nickel metal hydride batteries, which require only a hydrogen-oxygen recombination device and a backup pressure valve. Contaminants inside the cells can defeat these safety devices. Short-circuiting a battery will cause the cell to overheat and possibly to catch fire. Adjacent cells may then overheat and fail, possibly causing the entire battery to ignite or rupture. In the event of a fire, the device may emit dense irritating smoke. The fire energy content of cobalt oxide cells is about 100 to 150 kJ per Ah, most of it chemical. Replacing the lithium cobalt oxide positive electrode material in lithium-ion batteries with a lithium metal phosphate such as lithium iron phosphate improves cycle counts, shelf life and safety, but lowers capacity. As of 2006, these safer lithium-ion batteries were mainly used in electric cars and other large-capacity battery applications, where safety is critical. Lithium-ion batteries, unlike other rechargeable batteries, have a potentially hazardous pressurized flammable electrolyte, and require strict quality control during manufacture. A faulty battery can cause a serious fire. Faulty charges can affect the safety of the battery because they can destroy the battery's protection circuit. While charging at temperatures below 0 AA degrees Celsius, the negative electrode of the cells gets plated with pure lithium, which can compromise the safety of the whole pack. Battery packs which are not branded by a reputable manufacturer may not be built to the same safety standard as branded ones. While fire is often serious, it may be catastrophically so. In about 2010, large lithium-ion batteries were introduced in place of other chemistries to power systems on some aircraft. As of January 2014, there had been at least 4 serious lithium-ion battery fires, or smoke, on the Boeing 787 passenger aircraft, introduced in 2011, which did not cause crashes but had the potential to do so. Environmental concerns and recycling. Since Li-ion batteries contain no toxic metals, they are generally categorized as non-hazardous waste. Li-ion battery elements including iron, copper, nickel and cobalt are considered safe for incinerators and landfills. These metals can be recycled, but mining generally remains cheaper than recycling. At present, not much is invested into recycling Li-ion batteries due to costs, complexities and low yield. The most expensive metal involved in the construction of the cell is cobalt. Lithium iron phosphate is cheaper but has other drawbacks. Lithium is less expensive than other metals used. The manufacturing processes of nickel and cobalt for the positive electrode and also the solvent, present potential environmental and health hazards. Recalls. In October 2004, Kyocera Wireless recalled approximately 1 million mobile phone batteries to identify counterfeits. In December 2006, Dell recalled approximately 22,000 laptop computer batteries. Approximately 10 million Sony batteries used in Dell, Sony, Apple, Lenovo, Panasonic, Toshiba, Hitachi, Fujitsu and Sharp laptops were recalled in 2006. The batteries were found to be susceptible to internal contamination by metal particles during manufacture. Under some circumstances, these particles could pierce the separator, causing a dangerous short circuit. In March 2007, computer manufacturer Lenovo recalled approximately 205,000 batteries at risk of explosion. In August 2007, mobile phone manufacturer Nokia recalled over 46 million batteries at risk of overheating and exploding. One such incident occurred in the Philippines involving a Nokia N91, which used the BL5C battery. Transport restrictions. IATA estimates that over 1 billion lithium cells are flown each year. The maximum size of each battery that can be carried is one that has an equivalent lithium content not exceeding 8 grams per battery. Except that if only 1 or 2 batteries are carried, each may have an ELC of not more than 25 grams each. The ELC for any battery is found by multiplying the ampere-hour capacity of each cell by 0.3 and then multiplying the result by the number of cells in the battery. The resultant calculated lithium content is not the actual lithium content but a theoretical figure solely for transportation purposes. Although devices containing lithium-ion batteries may be transported in checked baggage, spare batteries may be only transported in carry-on baggage. They must be protected against short-circuiting, and example tips are provided in the transport regulations on safe packaging and carriage. For example, such batteries should be in their original protective packaging or, by taping over the exposed terminals or placing each battery in a separate plastic bag or protective pouch. These restrictions do not apply to a lithium-ion battery that is a part of a wheelchair or mobility aid, to which a separate set of rules and regulations apply. Some postal administrations restrict air shipping of lithium and lithium-ion batteries either separately or installed in equipment. Such restrictions apply in Hong Kong, Australia and Japan. On May 16, 2012, the United States Postal Service banned shipping anything containing a lithium battery to an overseas address, after fires from transport of batteries. This restriction made it difficult to send anything containing lithium batteries to military personnel overseas, as the USPS was the only method of shipment to these addresses. The ban was lifted on November 15, 2012. The Boeing 787 Dreamliner uses large lithium cobalt oxide batteries, which are more reactive than newer types of batteries such as LiFePO4. Research. Researchers are working to improve the research methods, power density, safety, cycle durability, recharge time, cost, flexibility and other characteristics of these batteries. See also, LIBs-air battery, potassium-ion battery, nanowire battery, solid-state lithium-ion battery, list of battery sizes, List of battery types, list of energy densities. References. Bibliography. External links, Lithium batteries at DMOZ, addressing the impact of temperature extremes on large-format Li-ion batteries for vehicle applications, National Renewable Energy Laboratory, March 2013. Application of life cycle assessment in nanoscale technology, lithium-ion batteries for electric vehicles, U.S. Environmental Protection Agency, April 2013. Cargo, lithium batteries, IATA.